In this video, we will cover logistic regression, how this algorithm is structured mathematically, and how we can implement it in Python from scratch. Hi, my name is Michael, and I run a blog called Inside Learning Machines, where I cover topics in data science and machine learning. My aim in this blog is to dive into machine learning algorithms and to explain how they actually work. You can find a link to my blog in the description below. Logistic regression is one of the simplest and most popular classification algorithms out there. And this simplicity is a great asset in terms of model explainability and the interpretation of results. Now, of course, we always need to know that the assumptions that underlie logistic regression are actually consistent and match with whatever problem that we're working on. Now here, I will first cover the key assumptions that underlie the logistic regression algorithm, and then we will walk through a description of how this algorithm actually works mathematically. Next, we will implement logistic regression into Python code and test that our implementation actually works. Now, if you stick around until the end of this video, I will also compare how our custom implementation performs versus the logistic regression that we can import directly from Scikit-Learn. So let's get started. So now we're going to go over the key assumptions behind the logistic regression algorithm point by point. So the first is that our target is categorical, meaning that it only contains discrete values. The next is that our independent variables are uncorrelated with each other. Next, we should make sure that we have enough training data to accurately represent the process we are attempting to model. And more specifically, we should have enough samples in our training data for each class in our target. Now, a little bit more on that. The classes in our target should also be balanced, meaning that we have roughly the same proportion of samples for the classes in our data set. And that just makes sure that during training, our model doesn't focus too much on any one particular class at the expense of others. Now, the last assumption we have here is quite interesting. It states that there should be a linear relationship between the independent variables and the log odds of the target. So let's look at that in a little bit more detail. Now, for the purpose of this discussion, I'm only going to consider the case where our target has only two classes. That's going to be 0 and 1. Now, if we can look at these two column vectors here, x and beta hat, x represents a single sample in our training data. More specifically, it represents a sample of the independent variables in our data. And these data have a total of m features, so this column vector has a number of entries ranging from x1, x2, down to xm. Correspondingly, beta hat also has a total of m entries in it, so from beta 1, beta 2, down to beta m. Now, if we compute the log odds of our two classes, so that is the ratio of the probability of getting a 1, so that's p1, divided by the probability of getting a 0, so that's here p0. If we encompass that in the logarithmic function, we should get a linear function of x, of our independent variables. And so what we see here are two column vectors multiplied with each other, plus an additional term, beta 0, which is our intercept. So this is the essence of our assumption here. This is actually what makes logistic regression a linear model. And actually, if we set this to 0, this represents the situation where the probability of getting either class is equal, so they're both 0.5, and that represents our decision boundary. So it's pretty evident from this that this assumption states that logistic regression will partition the data space in a straight line between the two different classes. So let's just keep this in mind as we move on to the next slide. So as I stated already, we're only assuming that we have two classes in our data. So let's now write out the functional form of the probabilities for these two different classes. Now, this is going to be governed by that last assumption that I focused in on the previous slide. And so to meet that assumption, I'm going to assume that these have the form of the logistic or sigmoid functions. So here now we see the probability of getting a 0 is represented by this exponential function, and the probability of getting a 1 is now going to be represented by this exponential function. So if we plot out these two different functions here for a range of the exponent values, so the exponent is just the combination of the model parameters and the independent variables, we see that for very small values, the probability of getting a 1 is low, it's close to 0, whereas the probability of getting a 0 is quite high, it's near 1. And as we get to larger and larger numbers, these functions start to converge, where at 0, they exactly meet. And this is our decision boundary. And beyond this, they diverge again. So this is quite interesting to see. Also make note that if we look at this plot, we can see that if we add up the two different probabilities at any point along the x-axis, they will equal 1. And so we can rewrite these two different probabilities in a simpler form. So we can just state that the probability of getting a 1 now is going to be equal to p, probability of for this class, as a function of x and beta. And now beta is a combination of our original model parameters, beta hat, plus the intercept, beta 0. So now this column vector has elements that range from beta 0 to beta 1 to beta 2, all the way down to beta m. And so now the probability of getting a 0 can be written in this form, and it will just be equal to 1 minus p of x beta. So you can see that if we just add up these two different probabilities, they will equal 1. Now to actually solve for what our beta column, our set of model parameters should be, we are going to make use of the maximum likelihood estimation procedure. And this involves forming up a likelihood function, then computing the derivative of that likelihood function with respect to our model parameters, beta, and setting that to 0. Now it turns out that that does not have an analytical solution, and so we need to employ an iterative technique in order to find a solution for our model parameters. So the technique that we will use is the Newton-Raphson gradient ascent algorithm. Now here, I'm not going to work through all the details of how this is derived. I do have an article on my blog that goes into all the details of how this is actually worked out mathematically. I have a link to that in the description below. You can check that out if you are interested in those details. Now here, I'm just going to go over the result of that derivation. So if we actually form up these mathematical objects, so the column vector y is just the list of our labels, our target. So our training data will just consist of n samples. So this column vector has a total of n entries in it, one target per sample. X is the total number of independent variables in our training data. And here we have M plus 1 columns. M is the number of features. N is the number of samples. And we have an additional column here, ones, and that's just for our intercept term. In addition, I'm going to assemble this column vector P, and that's just the probabilities for our classes per sample. Now, in addition to this, I'm also going to compute this diagonal matrix where each diagonal entry is given by this product. And so this is just the probability P multiplied by 1 minus P. Now, if we assemble all of this together and follow through with the approach that I outlined just before, we can come up with this update rule to find our model parameters. And so here we have the updated beta is equal to the previous version of beta, the version at the previous iteration, plus this term. And so we can iterate through our training procedure using this update rule to find where beta converges and to ultimately end up with the set of model parameters that is suited for our data set. So now let's jump into a Jupyter notebook and actually implement this procedure and then test it out and see that it works. Okay, so now that we're in Jupyter, we can start this off by loading in all the packages that we're going to need. So let's go ahead and execute this first cell to do that. Okay, now we can proceed to load in our data. So for this exercise here, we're going to be using the breast cancer data set that's available from Scikit-Learn. So we just have to execute this function, load breast cancer, and that's going to give us our array of independent variables, X, and their associated labels, Y. So let's run this. And just so you know, in Y, the way that the classes are indicated is that where Y is equal to 1, there we have an instance of a benign sample, whereas where Y equals 0, then we have a case of a malignant sample. So these are our two classes. So the first thing now that we can do with our data is do a train test split. So I'm going to be making use of the train test split function available from Scikit-Learn. And I'm going to be holding out 20% of the data for our test set. So let's just run this cell. Now the first thing I want to do is check to see in our training data whether the two classes are actually balanced or not. So let's just do a quick bar plot to check that out. Okay, and it's pretty evident from this that the classes are not balanced. So we should correct this. And the way that I'm going to do that is I'm just going to take the excess benign samples and I'm going to move that over to our test set. And then the end result should be that we have a training set where we have an equal number of cases of benign samples and malignant samples. So that's what this code block does here. So we just run this. And now that that is done, we can just redo our plot from before, our bar plot. And now we can see for our training data that in fact we have the same number. So that's good. Now, just for curiosity's sake, let's also do a similar bar plot for our test data. And here we can see that the excess benign samples have now been allocated here. So we do see that there's quite a lot of benign samples as opposed to malignant. We still have a fair number of malignant samples though in our test set. So it'll still be interesting to see what the results of our modeling is on these data. So now we can proceed by looking at our independent variables. So I'm just curious to see what kind of distributions are we dealing with here, and on what scales are these different features on. So the way that I'm going to do this comparison is by producing a box plot of our features, and I'm just producing the box plot for our training set. Okay, so here we have all our independent features, and it's pretty evident from this that the distributions do change between the different features, and the scales are certainly different. So that's important to keep in mind. Now, what I am interested in knowing is whether any of these features are actually correlated with each other. So to accomplish that, I'm going to produce a heat map to show how the features are correlated with each other in a visual way. Okay, so here's our heat map, and you can see right off the bat that our diagonal is lit up, and that's to be expected because the diagonal represents where each feature is correlated with itself, and so that should have a correlation of 1. Now, if we look at the scale on the right-hand side, see that this indicates the level of correlation by color. And so where we have white blocks or white cells, those are highly correlated feature pairs. And then as we get to darker colors, they become less correlated and then a bit anti-correlated. But it doesn't look like, based on this scale, that we really have a problem of anti-correlation. So it just dips to about -0.2. So it looks like what we need to be concerned with here is just cases of positive correlations. And so what we should pay attention to on this plot are the off-diagonal pairings. Now both sides of the diagonal are just mirror images of each other. So we can just focus in on one side. And it's pretty evident that we have some patches of features, off-diagonal feature pairs that are lit up, so we see some here and we see some more down here. And that's indicative of the fact that we do have some features that are correlated with each other. So that is something that we're going to need to address. And so in this next code block, that's what I'm going to try and do. So what I want to do here is filter out from our correlation data frame all the entries where our feature pairs have a correlation higher than 0.8. And then I'm going to group those together. So for every single feature, I want to see what features are highly correlated with it. And by highly correlated, I mean above this 0.8 threshold. So let's execute this. Now we have printed out to the screen our groupings. So on the left-hand side, we have each feature. So for example, here we have area error. And then on the right-hand side in the squiggly brackets, we have all the features that are highly correlated with it. So in this case, we have perimeter error, radius error, and mean area. And it's the same thing for each feature in sequence. So this groups together all the highly correlated features with each other. And now what I want to do is go through this list and remove, for every single feature, I want to remove out the features that are highly correlated with it. So that's what the next code blocks are going to do. So here I'm just going to determine a complete list of the correlated features. And now I'm going to cycle through our series that we computed up here above. And I'm just going to, on each iteration, I'm going to remove the features that are highly correlated with whichever feature we're at that given point. And then I'm going to just compile a list of the features that we need to get rid of, and that's going to be in to remove. So okay, these are all the features that we are going to remove from our set of independent variables. So let's go ahead and just do that by calling the drop function in pandas. We do that pretty simply. And now, just for curiosity's sake, let's do a box plot again of our training data. Okay, so here are features, and we still have a couple that are on different scales from the rest, so that's important to keep in mind for later on. So now we can proceed to actually implement our logistic regression. Now everything is going to be encapsulated in this class log_r. So first we have the initializer function, and here this takes two arguments: max iter, which specifies the maximum number of iterations for our training procedure, and then tol, which is the tolerance also for our training procedure. So those are stored here, along with what I have here, an array b, which just initializes the array for our model parameters. Now the next function, train, is what is going to train our model. So the input to this function is our training data. So xin is our set of independent variables, and then yn is the associated labels. So the first thing that I'm going to do is add a column of ones to x, and that is just for our bias term. Then I'm going to ensure that our labels are in the form of a column vector. And then I'm also going to initialize the model parameters. And now we're going to loop through the number of iterations that we've specified for our Newton-Raphson algorithm. So if we remember from the previous slide here, we define these different mathematical objects. So y and x are just our training data. Then we have also p and d, along with our update rule. So that's what we're going to implement now. So over here we have our p column vector of probabilities defined. And here we have our diagonal matrix. And now here we have implemented our update rule. And now this loop will terminate early if we exceed our tolerance. So that's how our training method is going to work. Now we also have a predict function, and that's going to be used to generate predictions once we've completed a training step. So here our input xint is just an array of our independent variables. And then also I have an input parameter called return prob, and that's a Boolean. And it just specifies whether we want to have the actual class labels returned or the raw probabilities. So the way that this function works is that we're going to add a column of ones for our intercept term, like we did before. And then I'm going to pass this through the logistic function. And that yields our probabilities. That's yp. Now, if we want to return the class labels, these are rounded. Otherwise, we just return the raw probability. And now the last function we have is called return b, and that's just used to return the learned model parameters. So let's go ahead and run this cell. Okay. So now, since we noticed that the different features are on different scales, and we noticed this when we were looking at our box plot before, we're going to need to scale everything. So standard scalar will just set all the features to have a mean of 0 and a standard deviation of 1. So let's use this now to scale the independent variables for both our training and test sets. Okay, and so now we can finally get to testing out our model. So first I'm going to declare an instance of our logistic regression. I'm going to train it, And then I'm going to generate predictions. And the first line here just generates predictions in the form of class labels. And the second line returns the raw probabilities. So let's go ahead and do this. And now let's compute the accuracy, precision, and recall for these results to get a quantifiable measure of how our model is doing. So okay, we have some results now, and these look pretty good. Especially the precision is very high, so that's nice to see. Let's produce a ROC plot. Okay, and this also looks pretty good. So these results look pretty nice. Let's take this to the next step now and run through the exact same exercise, but now using the logistic regression model from Scikit-Learn. So we're going to use the exact same data. We're going to measure the exact same metrics using the Scikit-Learn model. So let's go ahead and do that. I'm going to import first the Scikit-Learn logistic regression. And now, just like before, I'm going to declare an instance, train it, and then generate predictions. Now notice when I declare an instance, I'm also specifying that I want a penalty set to none, and that just specifies that we aren't going to have any kind of regularization with this logistic regression model, and that's just so that we have a fair comparison with what we implemented above, because no regularization was used. So we've got that, and now, like before, let's compute the same metrics and the ROC plot. Okay, and these results are exactly the same as what we got before. So this is very encouraging. This is a very nice result. It shows that, we've implemented everything correctly. And we have a working logistic regression model that we've implemented from the ground up. If you enjoyed this content, please like the video or subscribe to the channel. All the code presented here is available on my GitHub. Please see the description below for a link to that repository. If you would like to learn more about logistic regression and machine learning in general, please visit my site, insidelearningmachines.com. I have included a link to my article on logistic regression in the description below. Have a great day, and see you in the next video.